Hi everybody, hope your day is going well and that you guys are ready for our upcoming test on Thursday, or at least getting ready for that. The first concept that we covered in this particular unit was something called related rates. There's a wide variety of problems that can be given with this particular concept. Some of the areas that could show up would be areas of simple geometric shapes like rectangles, squares, circles. Your SOHCAHTOA relationship, your sine, cosine, tangent type setups in right triangles. You could do some similar triangles. You could do the Pythagorean theorem, the a squared plus b squared is equal to c squared. You could use the distance formula, where the distance is the square root of the x1 minus the x2 squared plus the y1 minus the y2 squared. For the volume of the 3D solids, typically those formulas would be given to you, whether they be cones, cylinders, or spheres, or they could give you some type of provided relationship where they give you the relationship in advance, and then they tell you to deal with how are the rates related to each other. And so the basic process goes as follows. You need to come up with a relationship that relates the physical quantities. Then you're going to take the derivative. With respect to time. Then you're going to plug in all your knowns, all the known values. And then finally you're going to solve for what you're trying to find. Typically in these types of problems, the hardest part of these is setting up the relationship that relates the physical quantities together. However, in previous years, students still, even though you go through this process, you do quite a few days of examples and problems, students don't always understand this particular process and procedure. And so make sure that you understand the process and the procedure, and so that you can successfully relate the rates once you come up with a relationship that relates the physical quantities to each other. We're going to go through one example, kind of see what happens. And so we have a little cone-shaped pile over here. Maybe we're at a construction yard, and basically people are using a conveyor belt and pouring maybe sand or something onto this conical pile. We know over here that the diameter of our base is always going to be, say, 3 times our height. The sand is being poured on. Basically, it is a change in volume. dV dt might equal something like, 5 cubic feet per minute. And they want to know basically what is dH dt. What is the change in the height? And again, for a problem like this, they would give you the formula for the volume of the cone. And that volume of the cone is going to be 1/3 the area of the base times the height. In this particular setup, I know dV dt because they gave that to me. And so if I take the derivative of this, I'll get a dV dt, and that's all good. I will get a dH dt when I take the derivative of that, and that's all good because I want to find dH dt. But the problem over here is I don't have a dr dt in my setup. It'd be very, very nice if I could get rid of this r variable and make my life a lot easier. Well, I know that the diameter is 3 times the height, and diameter is going to be twice the radius. And so if I solve for the radius is going to be 3/2 the height. I can take that value for radius and I can plug it in. And if I do that, the 3/2 times the 3/2 is going to be a 9/4. And you're going to get this volume is equal to this 1/3 pi 9/4 h squared times h. Finishing that all up, the 9 and the 1/3 are going to cancel, and you're going to get this 3/4 pi h cubed. This over here is basically step 1. You're relating the physical quantities to each other, and this is typically the hardest part in all these problems, is coming up with a relationship that relates these physical quantities together. At this particular point, I can take my derivative to relate the rates, and I get this dv dt is going to equal this 9 over 4 pi h squared dh dt. Again, h is not a t, and so when you take the derivative of that, you take the 3 down in front, you decrease the exponent by 1, you got to multiply by the derivative of what's inside, and the derivative of h is dh dt. At this particular instant, you could plug in the value for this dv dt. dv dt up here is going to be 5. You could plug in, well, it didn't tell us, or at least I didn't tell you guys. You can say when the height is maybe 10 feet. And so you could plug in this value for height over there, and then you could end up solving for dh dt. And that's basically the way this related rate problems go. You're going to relate the physical quantities, that's step 1. Take the derivative to relate the rates to each other. After that, you're going to plug in everything that you know. We know that dv dt is going to be 5. We know that h is going to be 10. And then we can solve for dh dt. And if we do that, we're going to get the 5 times the 4/9 multiplying by the reciprocal. And then we're going to get this divided by this 100 pi. And then you could simplify that. But this over here would be dh dt. The last thing we need to do is typically they're going to ask us for units. If you understand what's going on in terms of the context of the problem, a change in height is going to be a change in linear measurements. In this particular problem, it's going to be feet. A change in time is going to be in minutes. And so this particular item over here is going to be in feet per minute. But that's the basics of related rates. The only thing I can say with this is practice, 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 practice. Once you get to a point where you're comfortable and confident with it, they do go much quicker. The next section we come to is 3.1. In 3.1, we had a lot of very, very important information. One of the things that students struggle with is they don't have enough definitional stuff down. If you don't understand definitions, you are going to largely struggle with this test because you're not going to know what to do. And so as you're going through this next particular point over there, make sure you understand what these definitions are. For instance, the first definition that we really came to was something called a critical point. Most students don't actually understand what the definition of a critical point is. Basically, they get about half of it right, and they call that good enough. And so one of the things that you can possibly do is note cards, where on the front of the note card you could write, say, critical point. In the back of the note card, you could write what the definition is or what's super important about this. And again, what is a critical point? It's a point where the derivative of the function equals 0 or is undefined. And again, what most students do is they get half this definition right. And they basically understand that the function, the derivative of the function has to equal 0, but they forget the second half over there, or the derivative is undefined. And if you don't specifically know what these definitions are, it's really, really, really hard to answer questions on these particular things or to give justifications for something. Like if you find that x is equal to 2 is a critical point and someone wants you to justify why that's a critical point, you would say something like, this is the only point where, and again, call out the derivative by name. If you're talking about the function f of x, call out the derivative by name. Don't just say, hey, you. Don't just say it, but really call it out by name. And this is going to be f prime. And so this is the only point where f prime equals 0 or f prime is undefined. And again, make sure you're very, very clear with your verbiage with that, or you're going to end up with lots and lots of problems. And again, that is the biggest thing with this particular test, is really knowing all those definitions. And so when you get a question, you know what to do. Again, recommendation, go back to the self-assessment quizzes and go through those again. They cover pretty much every single concept that we did on the test. They basically are asking the questions, give a reason for your answer, explain, and you can always check your answers with the solutions in OneNote, or if you want to watch the video solutions, you can do that. The next thing we come to is the extreme value theorem. This extreme value theorem tells us that if we have a closed interval, there will be a biggest value and a smallest value if the function's continuous. And so if you have a closed interval and you have a continuous function, there will be a biggest value and there will be a smallest value to the function on that closed interval. This over here is paired very, very strongly with the candidates test. This candidates test tells us how we can find that extreme value. And basically the way the test goes is that extreme value can only occur at critical points or endpoints. Basically, your extreme value can only occur at critical points or at endpoints. And again, this particular definition uses within it another definition, which is why it's so important that you understand what these definitions are. And so again, if you're trying to find an extreme value, you could check the endpoints and you could check the critical points and you could figure that out. One of the things that students run into on this particular test is they're not very good with dealing with fractional exponents and things like that. And so if you had a problem where you had this f of x over here is equal to, say, x to the 2/3 power, and we had a closed interval between -1 and, say, not 4, let's do 8, -1 to 8, and they want you to find the absolute maximum value on this closed interval. How do you do that? And then they want us to justify our answer. And so based upon the candidates test, we know that these extreme values can only occur at critical points or at endpoints. And so our job is to find the critical points, if there are any of those, as well as the two endpoints. And so we're going to take our derivative, and we're going to get this 2/3 x to the -1/3 power, taking the exponent down in front, decreasing the exponent by 1. This over here is a 2/3 x to the 1/3 power. Does this particular expression ever equal to 0? And the answer is no. But there is a critical point if this was undefined, and it is undefined at x equals 0. And so we get undefined at x is equal to 0. That over there is a critical point. Then we're going to go out and we're going to check all those values. We're going to find the value of f at -1, find the value of f at 0, and find the value of f at 8. Again, if you're trying any values other than these values, it clearly indicates that you don't understand something fully, and you should be able to go to your equation and plug all these in. And so if we go and plug all these in, if you plug in -1, you're going to get 1. If you plug in 0, you're going to get 0. If you plug in 8, you're going to end up with 4. The cubed root of 8 is 2, and 2 squared is 4. And so they would want you to find, in this particular problem, say that maximum value, and you would say the max of f of x on the interval -1 to 8 is 4. And you want to give some type of justification for that, and you could say something like all critical points and endpoints were checked. Four was the biggest value. You don't need to refer to the candidates test by name, but it is a good idea to list it if you do remember what it is. And so you could say something like candidates test. Again, you don't need to refer to it by name. As long as you have the logic over there, you will get credit for it. But you need to have some type of verbiage that you understand that you check these critical points and you check these endpoints in order to find that value. And they're going to expect to see the logic and the worked out solution. And even though I know that 0 is not that maximum value, they're still expecting you to see that you actually found the value at 0. Okay. So that's that. The next thing we come to is 3.2, which is Rolle's theorem and the mean value theorem. Rolle's theorem had three conditions for Rolle's theorem and then 2 for the mean value theorem. Rolle's theorem required continuous on the closed interval, differentiable on the open interval, and required that the two endpoint y values, f of a was equal to f of b. Then, if that was true, f prime of c is going to equal 0 for some c that is between a and b. For, I guess, some c such that, there we go. But that's what Rolle's theorem does. And then the more important theorem over there between Rolle's theorem and the mean value theorem would obviously be the mean value theorem. Rolle's theorem is a specific case of the mean value theorem. The mean value theorem has just the first two conditions, which is continuous on the closed interval, differentiable on the open interval. And if both of those things are true, then the derivative, the instantaneous rate of change, is going to equal the average rate of change, the slope between the two endpoint y values, the endpoint values. And so this over here is going to be instantaneous. And this over here is going to be the average rate. And so again, the mean value theorem guarantees that there will be that point where the instantaneous rate of change is equal to the average rate of change for some c such that c is between a and b. And that's your mean value theorem. And again, there's lots of different ways that you can do mean value theorem problems. They can ask you to find the value for c that's guaranteed by the mean value theorem. They can ask you to assess the existence of a point. Does this particular point exist? And again, we have a couple of theorems that refer to derivative values, and we have a couple of theorems that refer to y values. And so the extreme value theorem reports to the existence of a y value. Another one that reports to the existence of a y value is the intermediate value theorem, the IVT, which we covered in a previous unit. And then these two over here, mean value theorem and Rolle's theorem, they guarantee derivatives are equal to something. And so again, look what they're asking you to find. They're asking you to find the derivative of something equal to something, or they're asking you to find a y value equal to something, and that will help you to distinguish which of these four existence theorems you're supposed to use. But a very simplistic example is if you had some f of x is equal to, say, x squared, and they wanted to find the value guaranteed by this particular theorem, the mean value theorem, maybe on the interval between 1 and 9. And so if we did this, we could find the two y values. And so we know that f of 1 is going to be 1, and f of 9 is going to be 81. If we find the average rate of change, we're going to get this 81 minus 1 all over 9 minus 1. This is going to be 80 over 8, and this over here is going to be 10. And so over here, if we find our instantaneous rate of change, this f prime of x, that's going to be 2x. And there will be a point where this instantaneous rate of change is equal to this average rate of change. When does the 2x equal to 10? That would obviously be when x is equal to 5. And that's finding the value that exists. They can ask you to justify different existence of values, where they can give you some tables of values, where they give you some x values and some f of x values, and maybe they give you 0, 10, 3, and 33. And they say, is there a point where f prime has to equal 3? And you could go over there and you could find the slope between some of the values in the table. The 33 minus the 3 is going to give you 30. The 10 minus the 0 is going to give you 10. And if you do this 30 over 10, you're going to get 3. This mean value theorem would guarantee that this over here is true for some value. And they typically don't write x there. They typically write c. If the two conditions for the mean value theorem are met. If it's continuous on this closed interval between 0 and 10, and if it's differentiable on the open interval between 0 and 10. If they don't tell you enough information to figure that out, then there would not be a guarantee that this particular value exists. Some of the ways that they deal with that is they tell you have a differentiable function, and a differential function would obviously imply that the function is also continuous. But that over there is Rolle's theorem and the mean value theorem. The next thing we come to was section 3.3. And again, this gets into largely definitional stuff where we're doing this 3.3 and 3.4 as far as our units go. We have some first, and I'm just going to put these both together because they're both really similar in terms of what they talk about. But we have some first derivative items and we have some second derivative items. And you need to understand what each of these particular items mean. And again, these are definitional items, increasing, decreasing. And again, you probably want to make a note card or do some other type of activity where you very strongly know what these particular items mean. And so what does it mean for a function, and we'll talk about f, to be increasing? This word increasing means the derivative of this particular function, the function of interest, is going to be positive. And so this over here means that f prime is going to be greater than 0. If we're talking about a different function, if we're talking about, say, g double prime, we want to know when g double prime is increasing. We got to find the derivative of g double prime, and it's going to mean that g triple prime is greater than 0. Increasing means the derivative of something is positive. Your question is to figure out what are they talking about, and then find the derivative of that, and then find when that is positive. Decreasing over here means that the derivative of something is negative. And so if we're talking about the function f, it would imply that f prime is going to be less than 0. If we were talking about the fifth derivative of something, it would imply that the sixth derivative of something is less than 0. Again, the word decreasing just means that the derivative of something, the rate of change of something, is negative. And again, these are very, very important keywords. And again, make sure that you guys can figure out these pieces. The next thing we come to is our first derivative test. The first derivative test allows us to identify relative extrema. And so we would want to know, in terms like of a relative max and a relative min, how would I identify that? How would I identify the relative max of f? Again, a maximum means that the function was going up, then the function went down, the function was increasing, then the function was decreasing. But that's typically not what we do when we solve these problems. And so you really want to talk about what's really going on. What's really going on is f prime is greater than 0, then f prime was less than 0. At this particular point over there, the derivative of the function of interest, and call it out by name. Don't just say, hey, you. Don't just say it. Call it f prime or f double prime or f triple prime, depending upon whatever function you're dealing with. F prime changed from positive negative at maybe x is equal to 10. And then call out the relative max that way. The relative min of a function f is going to be when the derivative of f changes from negative to positive. And so again, that's going to look something like this, where over here in this particular region, the function was going down, the function was decreasing. More importantly, the derivative of the function was less than 0. Then the function was going up, the function was increasing. More important, the derivative of the function was positive. And so when the derivative of the function changes from negative to positive, that's when you get the relative min. If you don't have that change in signs, you would not get a relative min or a relative max. These relative mins and relative maxes can only occur at critical points where the derivative is undefined or equal to 0. You cannot change sign unless a function is undefined or equal to 0. Again, be very, very careful in your verbiage when you talk about these. Identify the function of interest and then talk about it. If they want you to find where f double prime has a relative min, your explanation should be talking about f triple prime. And so you'd say something like, this is the only point, or these are the points where f triple prime changes from negative to positive. Or you can say at x equals -2 or x equals -5 or x equals 10, f triple prime changes from negative to positive, and that's why you get a relative min. Again, this is not super hard, but again, it's something that students do struggle with. I don't really know why they struggle with it so much, other than the fact that they really don't have these definitional items down as strongly as they should have. What goes along with this is, again, you have to be able to deal with your fractional exponents, your rational functions, and things like that. A lot of these problems are going to be polynomials, but the fractional exponents definitely are going to show up. Those are the only ways you can really get a really good assessment for if students understand stuff or not. And so again, make sure you can deal with your fractional exponents, make sure you can deal with your negative exponents. And for instance, what if you have f of x is equal to, I don't know, maybe x plus, say, 1 over x. I'm not sure what they're going to ask for. Let's say they're asking for a relative min. See if we have any relative mins. In order to do that, we'd have to find our derivative. Our derivative is going to be this 1. This over here is an x plus x to the -1 power. And so we're going to get this minus x to the -2 power, which is a 1 minus 1 over x squared. This is undefined at 0, but that's not a critical point because the original function wasn't defined at 0. At x equals 0, we have a vertical asymptote using our limit information. At that particular undefined value, we have unbounded behavior, and there's a vertical asymptote there. But does this function ever equal to 0? And if you multiply both sides by your common denominator, you'll get x squared minus 1 is equal to 0. So x squared will equal 1, and x will equal plus or minus 1. If we try to analyze our derivative, we have -1, we have 0, we have 1. At 0, we have a vertical asymptote, and we're going to need to figure out what happens at each of those intervals. And so if you plug in values like large negative numbers in magnitude or large positive numbers in magnitude, the 1 over x squared will be very close to 0, and 1 minus that is going to be positive. If you plug in values between -1 and 0 or between 0 and 1, the 1 over x squared is going to be very, very large in magnitude. 1 minus that is going to be negative. And so the function f was going up, then it went down, then it went down, then it went up. If they ask you to find a relative minimum, the relative minimum is going to occur at x is equal to 1. This is the only point where the derivative of the function, which is f prime, call it out by name, this is the only point where f prime changes from negative to positive. Or at the point x equals 1, f prime changes from negative to positive. But again, try to use it by name and try to call it out by name. If they ask you where is f increasing, you could say f is increasing from negative infinity to negative 1 and from 1 to infinity. What's the reason for that? Because f prime is greater than 0 on these intervals. Again, make sure you understand these definitions because you will be asked to give a reason for your answer, explain, etc., etc., etc. Okay. You should be able to deal with graphs, and again, this kind of comes into play where you might have something over here where this is the graph of f prime, and they might do something like this, where this is, say, negative 2, 0, 1, 2, 3. And they might ask you, where does f have a relative max? And again, you have to understand what these definitions are. And the first step is always, what do I need to find? Well, in your mind, you're saying relative max of f. I need to find where f prime changes from positive to negative. Okay, what did they give me? They gave me a graph of f prime. Okay, how do I use this graph to find out where f prime changes from positive to negative? Well, that happens when the y values change from positive to negative, and that's going to happen at x is equal to 3. And so at x is equal to 3, there's going to be a relative max on the function f. And again, just be prepared to deal with those derivative graphs. You also have all the second derivative relationships. You have concave up and concave down. Again, these are note card worthy items. And again, what is the meaning of concave up? When is the function f concave up? That's when the second derivative is greater than 0. And again, just be careful. If they're talking about f, the second derivative is f double prime. When is it concave down? If they're talking about f double prime, it's going to be when the fourth derivative is less than 0. Again, it's the second derivative of whatever function they're talking about. And so over here, normally they ask about f, but they can ask about any function. Just remember, it's the second derivative of whatever function they're talking about. And make sure you call out these functions by name. Inflection points, we'll write that one out. Inflection points occur where the second derivative changes sign. As long as you get that down, you're going to be good for this class. They're never going to give you a case where you don't have a tangent line of something. Typically, you're talking about twice differentiable functions. So you don't really run into the category. In this particular class, all that matters is the second derivative change sign. There is an additional condition, which is why I keep mentioning it. That doesn't show up in AP Calc. It's going to show up in subsequent math classes. I typically don't like to tell you something that's wrong, and so I will tell you that there is that exception if there's not a tangent line. And so again, there's different ways of doing this. If they give you some function, say f of x is equal to like x cubed minus x, let's do x squared. When does this have an inflection point, or where does this have an inflection point? Can't find the second derivative without finding the first derivative. We got to find the first derivative, which is going to be this 3x squared minus 2x. Then we can find the second derivative, which is going to be this 6x minus 2. And then we could basically figure out when does this equal to 0. And x over here is going to be 2 over 6, or 1/3. And so when would this have an inflection point? Possibly at 1/3. We should really check it out. We should analyze it. And if we look over here and try to analyze our second derivative, does it actually change sign? And the answer is yes, it does go from negative to positive. And so you would get that sign change over there. The point x equals 1/3 would be an inflection point for the graph of f. Again, make sure that there's a change in sign, because if there's not a change in sign, you're going to have issues with this. Um, okay. The other way that they can do this is they can give you that graph of the derivative. They can do something like this, where this is -2, this is 0, this is 1, where that's right up there at the peak. This is 2 and this is 3. This is a graph of f prime. And they ask you the question, where does f have an inflection point? And again, you have to figure out what are they asking. They're asking about f having an inflection point. What does that mean? That means the second derivative of f has to change sign. Okay, how do I find the second derivative of f given this? Well, the second derivative is the slope of this particular graph. My slopes over here are positive, then 0, then my slopes are negative. Do these slopes ever change sign from positive, negative, or negative, positive? Yes, at x equals 1, they change sign. X equals 1 is an inflection point on the graph of f. And so over here, we would get that x is equal to 1 is an inflection point for f. Since what? And again, call it up by name. Don't use the word it. How do you get inflection points? You're talking about the second derivative of something. Second derivative of what? Second derivative of f. Since f double prime changes sign at x equals 1. That's why that's an inflection point. The next thing we run into is something called the second derivative test. What the second derivative test tells us is if I have a function where I have a horizontal tangent line and the graph is curved down, you're going to get a relative maximum. If you have a horizontal tangent line and the graph is curved up, you're going to get a relative minimum. And so this relative maximum happens because f prime is equal to 0 and because f double prime is less than 0. This relative min happens because f prime equals 0 and f double prime is greater than 0. But that's your second derivative test. Typically this test works very, very well if you don't know what's happening on both the right and the left side. If you know what's happening on both the right and the left side, I recommend using the first derivative test. F prime is positive. F prime is negative. Because f prime changed from positive to negative, you got a relative max. F prime is negative. F prime is positive. Because f prime changed from negative to positive, you got a relative min on the graph of f. Again, the second derivative test works well if you don't know what's happening on either side. Typically, tables of values are a great way for that, where you may know a bunch of different values. Someone may tell you you have f prime, you have f double prime, you have f triple prime, and maybe you have 10, 0, -2, 3. Does f have a relative min or max at x? This is x, say x equals 3. Not 3, let's do a different number. X equals 1. Does this function f have a relative min, a relative max, or neither at x equals 1? And then we look over here and say, hey, I have a horizontal tangent line. Hey, this graph is curved down. Horizontal tangent line, curved down. That must be a relative max. And then justify it. Why? What's the justification? Again, because f prime of 1 is equal to 0, and f prime of 1 is less than 0. Or you could say f prime of 1, which equals -2, is less than 0. But that's our second derivative test. Is there anything else? No, that's kind of what I want to go through for the review. There's a lot of information here. There's a lot of analytic steps as to go through. Again, my recommendation is practice, practice, practice. But whatever you do, make sure that you know what these keywords are. Like second derivative test, have a note card for it. What does it say? How do you show that? How do you use that? How do you find that? How do you find that? How do you find that? Because if you don't know where to start on this particular test, all the problems are going to look the same, and it's going to get very, very messy. It's going to get very, very ugly. Again, this is a test that students can do very well on. It is a no calculator test. Again, if you have questions, try to reach out to me. I'll do my best to help. But again, make sure you understand those definitions so you know what to start, or know where to start, and you know what you're trying to find. And you'll do significantly better with that. Hope everything goes well.